Hello, and welcome to Enhancements in Visualization. My name is Brett Champion, and I'm joined here by Jose Martin Garcia, and we're going to be talking about what's new in the Wolfram language for visualization and geocomputation. I know we have a wide range of people with different experiences with the Wolfram language, and so most of these talks are going to assume some experience. If you're relatively new to the system, I've included in my notebook, I think, 3 good introductions to the language itself and the visualization functionality within the language. And so these are the 3 links, and the first is for our online documentation, which has everything that we have in product. It's the full documentation available online. The second is Stephen Wolfram's Elementary Introduction to the Wolfram Language, which is a book that he put out recently and is also available to read online. And you can try the examples in the Wolfram Cloud. And the third link that I included is to a sort of on-demand presentation about graphics and visualization in the Wolfram language. And so now we'll go ahead and move on. So one of the features that we added in version 11 was, or not added per se, but extended and revamped a bit, was the ability to remove singularities from when you're plotting functions. And this was originally added in version 6 for certain classes of jumps and piecewise discontinuities and branch cuts. And for version 11, we extended it to include poles and essential singularities. So the sort of most obvious and most easily understood, going all the way down to middle school math, is plotting 1 over x or plotting tangent of x, where we automatically remove the asymptotes that would normally be shown by most calculators or other software systems. And so this just happens automatically, and we automatically figure out where those are and make sure to remove them. This is controlled by an option called exclusions, and if I said exclusions goes to none, I actually need to, no, that wasn't reevaluated. Then if I said exclusions goes to none, then you see the asymptotes that aren't really part of the curve. They're just an artifact of how such things are frequently drawn. The 1 over x example, it coincides with the y-axis, and so it's a little bit hard to see in that case. And we also have exclusion style, which means that we can control the appearance of the asymptotes if we do want to show them. So in this case, I've said exclusion style goes to red, and the asymptotes are now showing up as red, where those singularities occur. And of course, it's way more, I mean, we handle things that are way more complicated than just tangent of x and 1 over x and simple functions like that. So here we have Pochhammer with sine and Bessel J, and everything introduces, sort of its own set of singularities, and end up with, sort of funky little curves that nobody has ever seen before. And it isn't just restricted to curves, so it also goes into sort of all across our visualization functions. And so here we have a plot of a 3D surface, and I have x squared plus y squared minus 1 in the denominator. And so we have a singularity that is all around the unit curve. So if I rotate this, you can see where it sort of split that surface. And I like this one because it has that xy in the numerator, and so that goes from positive to negative, and then as it crosses that circle, it flips, negative to positive. Ends up looking kind of cool, I think. And so that was something that we added, about a year ago. And now I'll move on to labeling and callouts, this is sort of an ongoing project as we roll it out to more and more functions in the system and gain more experience with it and get better optimization and better speed on how to position the labels in ways so that they don't overlap. So here I have, I get a list of all the countries in Europe. This orange rectangle, for people who may be new to the system, is our interface to a natural language interface to our collection of data. And you get it by using Control= as the keyboard shortcut. And then for each of those countries, I'm going to get the GDP and the government debt. And then I'm doing this, I'm putting those in a log-log plot. And so I have the GDP and government debt, and I have the list of countries, and it's going to automatically use the countries as labels for each of those points. And you can sort of see how they're nicely distributed, and the labels, especially in this case, are doing a good job of not overlapping. And that's all handled automatically. And you may also notice that there's a few points that don't have labels, that don't have callouts at all. So like this one in the top right corner, you sort of ran out of space for a good place to put the label. And so if I mouse over it, then I get a tooltip, and we see that that point is Germany and United Kingdom down here below France. So the callouts have a lot of flexibility in how they look, and you have a lot of control over making them look and applying different styles to them. So here I'm just using a simple appearance goes to balloon, which gives it sort of a little speech bubble sort of appearance for all the labels. And the ones that aren't labeled still have their tooltips associated with them. Everything else is the same in terms of this plot. It's still a log-log plot, same data set, that sort of thing. Here's another example, just sort of really showing off a lot of the flexibility that we have for callout. So we have two curves that we're plotting, sine and cosine, and for the callout, we're using the balloon appearance as before, and we're setting the background of the respective callouts to match the curve style, and we're having the label text be white in this case. One other aspect of this is that in this case we're using callout as a wrapper around our function that we're plotting. And this gives us sort of the finest grain of control, whereas the previous examples were using callouts in a way where you specify all the callouts at once and they are sort of getting, everything has a callout. In this case, by using the wrapper, we could have only selected curves or selected data points having the callout. And I think this is a good time to go ahead and look at the documentation somewhere. Good help. So here is the documentation for callout, for example, and for people who haven't seen our documentation before, who are new to the system, we try to have very complete, thorough documentation as much as we can. And so we have the different positions, we have that you can sort of where to place the callout relative to a point or curve. We have callouts to sort of, sorry, not callouts, diagrams to help us identify the different components of the callout for documentation purposes. Here are all the options that are available to callout, and the components of the callout that they are sort of controlling. Here's a gallery of the built-in appearance settings. So a lot of stylistic control there. More and more documentation, and then sort of lots of examples showing it with a wide range of functions, different styles, that sort of thing. And so especially with the visualization functions, we try to be as complete as possible and provide lots of examples. And so if you aren't sure if something can be done, I always find it useful to open the documentation for the function and just scroll through the examples and see what looks close to what I'm trying to do and use that as a starting point. So for version 11.1 earlier this year, we added callout support for a lot of the charting functions, bar charts, pie charts, bubble charts. And we're going to take a look at an example of each of them. And so here we have the life expectancy for all the NATO countries. And it's being presented as an association, which is this sort of item goes to value sort of structure, this rule structure. And bar chart is going to consume that automatically, and so there's a couple things we're going to do. We're going to set chart labels goes to automatic, which is going to use these as the chart labels along the axis here. And then we're going to use labeling function, which is an option to bar chart and many of the other visualization functions, to construct a callout where, in this case, that little hashtag sign, which we call slot, corresponds to the actual value. So for Turkey, 75.259 years. And then if we look at Turkey, we see that it's labeled with a callout with the exact value corresponding to it. So you don't necessarily have to trace your eye all the way down to the axis to read off the value. We're directly labeling each of the bars in this case. And we can do the same thing with pie chart. In this case, rather than labeling each sector of the pie chart with the value, we have callouts that label them with their country. And again, the text for the callouts are all positioned so that they aren't overlapping, which makes it easier to read. And then we're using the leader lines on the callout to connect the text back to each of the respective sectors. And then this example for callouts is going to be bubble chart. So bubble chart takes sort of 3 numbers per data point, an X position, a Y position, and a size. And so we're looking at male life expectancy on the X-axis, female life expectancy on the Y-axis, and the bubbles are going to be sized according to the population. And again, we have an association here, and those are going to provide the labels. And the interesting thing with the bubble chart is that if the bubble is sort of large enough relative to the label, callout has the ability to put the label inside the bubble. So we see that for Turkey and Spain in this case. And the others get the text outside with a leader line connecting back to the disk. And we get a little bit of conflicting tooltips here. One has the population, but somehow if I hit the right spot, I can get the country name as well. So in this case, Norway is that smaller circle on top of Canada. And so far I've looked at the exclusions mechanism for removing singularities and the callouts, and those are systems that go across I mean, either as all the visualization functions where it makes sense, or that we're in the process of rolling out across all the visualization functions. And now I'm going to take a look at some of the newer domain-specific visualization functions that we've been working on. And so here, left upper limb is sort of a large collection of muscles and bones and ligaments and veins and arteries, and by default they all get sort of a perhaps not what they actually look like, but something that is what people would characteristically expect them to look like for illustration purposes. But there's a lot of ability to sort of override that, and we do that using a function called anatomy form, which basically sets up some state on how to color elements that follow it. So in this case, we're saying that anything that is muscle is going to be gray. You can sort of see everything that was red up above is sort of gray in this case, with the exception of the left deltoid, which we want to be cyan. And so we can use that to sort of highlight that muscle or group of muscles in the visualization. And the thing that I think is interesting about this, or one of the things that I think about is interesting about this, is that we're sort of mixing different types of things. And so here, muscle is a very general concept. I mean, there are lots of things that are muscles. Whereas the left deltoid is something that's very specific, and so you have like a class of things versus a specific instance of that thing. And you can apply styles to any combination of those sorts to those that you want to. I suppose I should point out that this is a 3D object. I can click on it and rotate and see what the extent of that deltoid is from different angles and that sort of thing. And then coming in version 11.2, we've added plot themes, which is a general mechanism we have for the visualization functions, to Anatomy Plot 3D. So here is one that simulates what an X-ray might look like. It is not necessarily a faithful, completely accurate representation, but we're able to get the general effect, and it's set up so that bones are more opaque and show up better than muscle or other soft tissue does, similar to an actual X-ray. That's a little bit bigger, a little bit heavier to rotate, so it took a moment before it actually started. And then the last theme that I want to look at for Anatomy Plot 3D, and we actually have a few of these, but scientific is the easiest one to get to, is one where every structure in the plot gets its own color. And in addition to everything getting its own color, everything is also getting a tooltip. So we see that this green area is the clavicular part of the left deltoid. And then the orange is the acromial part of the left deltoid. And sort of all this information is available through our knowledge base, and we're able to sort of include it in these graphics in sort of a nice way using these themes. And so now we'll move on to feature SpacePlot. And this has sort of come out of a lot of the machine learning work that we've been doing recently, and possibly some of you have been in our earlier seminars about machine learning. And so feature SpacePlot is trying to sort of tackle the problem of, if I have a large data set with lots of different properties or a large mixture of different types of data, how can I try to make some sense of that and create a visualization out of it? And so the first two examples are going to use as input the flags for every country in the world. And And so I just take these, and so flags here is just a list of images, and I feed it into feature SpacePlot, and by default it's looking at the images, and it has special code that's exposed through dimension reduce and feature extract and that set of functions on how do we interpret images by default. And so in this case, what it's doing is it's looking at, well, okay, up here are all the images, all the flags that have horizontal stripes. Down here are all the ones that have some form of cross in them. Over in here, we have some of the vertical stripes. The British Empire is all down here at the bottom, all clustered together. Very similar flags. Off on the left here, we have horizontal stripes with sort of a triangle on the left-hand side. And I didn't tell it anything about how to group these flags. It looked at the data and decided, okay, these are how the different bits of data are similar, these are how they're different, and here is sort of a grouping to sort, as a sort of almost a clustering operation sort of thing. If you use a different extractor, then you get a different effect. And so in this case, we turn the images into a list of pixels, and it turns out that it's effectively then groups by color. And so you have sort of all the red down here in the bottom, and dark blue at the top, and lighter blue off to the right, and green is sort of up here below the dark blue. And then, anything that isn't predominantly one color or the other gets sort of scattered in different ways. And so I think these examples are sort of interesting in terms of simplicity of input and simplicity of output and being colorful and easy to look at. But I wanted to look at another example. And so here we have, for every country in the world, we get its life expectancy, GDP, population, birth rate, bank loan rates, inflation rate. You can have lots of additional things here. I just picked sort of a range of economic and demographic information. And I fed this into feature SpacePlot and got an interesting result in sort of how it what it put next to each other and what it didn't. And here I'm saying that I want the points labeled with callouts. And so the points didn't quite allow as many callouts in the bottom right corner, but if I look at this, then sort of we have France and Japan and Germany and the UK. Sort of the strong economic powers of the world, or at least many of them. And then over here on the left, we have a bunch of countries that aren't necessarily as strong economically, more developing perhaps. And then the outliers are also interesting. So we have the US here, sort of off on its own, Brazil and Russia and Indonesia in the cluster here. India and China are practically on top of each other, off by their, off on their own in one part of the plot. And it's sort of interesting to see sort of how the algorithm decided to take this mishmash of data and try to apply some order to it and apply some structure. And then you can look at it and sort of see, okay, this is the well-developed countries, these are the developing countries, these are sort of notable outliers in India, China, the US, that are sort of large and on their own, there can't be that many Chinas in the world. So that finishes my portion of the talk. I'm going to pass it over to Jose, While we're doing that, there's going to be a quick poll that we'd appreciate you taking just for some feedback for us and better understanding our audience. And after Jose has finished, then I'll come back and we'll answer questions all at the end. So, thank you.
Okay, this is Jose Martin Garcia. I will continue now and talk about the recent additions in the functionality for geo-visualization in the Wolfram language. We are now getting the results of the poll sent, and so we see that many of you have already experience with Mathematica. About a quarter of you don't have experience with Mathematica, so I hope I'll have an introduction to the general geo functionality with Mathematica. So, and I hope this is a good intro for you before we go into newer functions. Okay. So this is the summary of what I'm going to talk about. So first, as I was saying, I will give a short intro to the geo functionality in general in the Wolfram language, and then I will focus on the recent additions since version 11.0. In particular, I'm going to introduce a function and a new set of data in 11.2 that we will have very soon. And then I will talk about another function called GeoBubbleChart, which is the version for geo-visualization of what Brett presented before. And then we will talk about GeoHistogram. The geo framework in the Wolfram language is basically divided in 4 big sections. So we have data, then we have the geodetic computation functions, geo-visualization, which will be the main topic in today's talk, and then also functions for statistical analysis of data. So the geodata is controlled through the same framework that Brett showed before, the entity framework, in which we have objects with this structure, always a domain, and within that domain, a name that identifies the entity. This is a very general and systematic way of presenting entities and provides access to the really large knowledge base of Wolfram Alpha. So here we have, for example, the entity that represents the United States, and then we can query it for any property, like the GDP, say, for example, here. So there are hundreds of domains, and many of them related to geo, and then for a domain like country, there are also hundreds of properties that you can query for each of these entities. The results can be of any type in the Wolfram language, including numbers, quantities with units, images, mathematical expressions. So for example, in this case, we are getting an image of the International Space Station. So satellites are one of these domains in the entity framework. Okay, so then in geodesy, we have our fundamental object, which is geoposition, that defines a geolocation with a latitude and a longitude in degrees. And so here, for example, we'll use GeoIP, or if this is evaluated in the phone, this will use your GPS, etc., to give you your location. For any entity, we can find its location. It's one of its properties. And we can also then convert that geoposition value into the coordinates corresponding to any other, to any projection, say the Euler's projection, etc. We have functions to compute distances, this distance along a geodesic, and the result is given back as a quantity. Notice that it's giving me the result back in miles because I'm in the United States. It would be in kilometers, for example, if I was in Central Europe, say. There are functions to compute destinations. So if I'm here and I want to move 5,000 miles along a geodesic starting with a bearing of 35 degrees, I will end up in this point, which I can plot in a map and happens to be in Belarus. Okay. In geovisualization, the fundamental object is geographics. Geographics is the low-level way in which we can construct maps, and it's based on a combination of giving a collection of what we call geoprimitives with directives controlling styling aspects, and then options to control the result of the map. So here we have a geographics containing a geodisk centered here in Champagne and with a radius of 800 miles. And then we have a path colored in red from here to London and then to the position before the position we computed before in Belarus. And for example, this is an example of a geo option in which we are adding grid lines. And notice that the system is choosing automatically the projection, the spacing between the grid lines, and the zoom level for the background image, etc., etc. So many functions in the system use geodata, and they are all using the same language, of course. So for example, we have a function that computes or returns data related to eclipses. And so for the eclipse that happened a couple of days ago, we can return, say, the polygon of totality, given as a polygon with these locations. You see here the bounds in latitude, longitude, etc. This was the polygon of partiality. And just to add something else, here we have the line, which is the path of the orbit of the International Space Station, centered more or less at the time that it was crossing that point. So this is one orbit, and it orbits around 90 minutes its time. So here we have like 2 full orbits. Okay. Then we have many other functions for geovisualization. We have GeoListPlot and GeoRegion Value Plot from version 10. And later, I'm going to present 2 new ones which have been added more recently. For example, here we have, again, a collection of positions for data that we have for this new domain of entities, nuclear explosions. And here we can plot them directly, very easily in a map of the world. And finally, the 4th section is about spatial statistics. And here we have several functions. This is one of them that computes, given some locations, compute what's the location on the Earth that would minimize the sum of distances to all of these locations. So for example, from these 5 points, the point happens to be very close to the North Pole. And I'm using here the azimuthal equidistant projection, which preserves distances from the center point, in which I've put the so-called median point. Okay, so this was a very brief introduction to the geofunctionality. And now I'm going to talk about these 4 additions in Wolfram Language version 11. So the first one is the function GeoImage, which is a function that will be in the system for version 11.2. So geographics and the other visualization functions have a image as background. So the main purpose of GeoImage is giving you directly that image. So in geographics, this is a graphics, and here we can use primitives and add other things on top of it. This is an image, right? And for example, we could now use the image processing functions to do various things with it. GeoImage is able to connect to external providers of tiles, and this allows us now to go much deeper in zooms. For example, this is an image of Rome around the Colosseum with a range of 2 kilometers. And we can go even deeper to a range of like a quarter of kilometers, and you see we see now perfectly the shape and the three-dimensional structure of the Colosseum. So here we are using the digital globe, external geoserver, and this feature in Wolfram Language 11.2 will be experimental. So in the future, using external services, as some other external services in the Wolfram language, will require the use of service credits. In version 11.2, this is free. This is another example I have here, which is that of one of the antennas defining the ITRF93 datum. So the Wolfram language contains a large collection of datums as well, and so we can provide the numbers. These are numbers in meters in a XYZ coordinate system center at the center at the origin of the ITRF93 frame. And then geoposition can convert that into latitude, longitude, and elevation in meters with respect to the ellipsoid of the ITRF93 frame. And for example, we can also convert it now to the standard datum used by the Wolfram language, which is ITRF00. In this case, the latitude and longitude change very little, but and there is a change in elevation, small change in elevation. So if we plot if we show the image around this antenna, just by giving the position, we get that. And we see that the base would be at the center of the image. Okay, so this was another example to show how deep in zooms, basically zoom 18, if zoom 1 is the whole Earth, we can go now with GeoImage and the access to the external provider. The second addition is geo-elevation data for the moon. And before we had satellite images for the moon. Now, that's an orthographic projection of the data. This is equirectangular projection showing the whole moon. Now we have also geo-elevation data, and we have up to zoom 7 here for the moon. And this is a rainbow, basically rainbow color function relief map of the moon. And so we see this is basically the face being in front of us. So we see how the other side of the moon contains higher elevation and also lower, the lowest point and the highest point. Something interesting here is, well, if we take some sort of profile of the elevations of the moon around, so we start here and we go around, we go back, we see this type of shape. This is bringing all the elevations as a quantity array in meters, and these are numbers measured from the center of the moon, so about 1,700 kilometers. And the variations are of the order of 10 kilometers or so. And if we plot that, it's possible to see the variations. So this is something that was possible to photograph the other day during the eclipse, the small variations, and these effectively produced the famous Bailey's beads that we were all photographing the other day. It's also possible to produce region objects of using the elevation data for the moon. And this is an example of a mountainous area of a disk around this point of 100 kilometers radius. Okay, Now let's have a look at GeoBubble chart. So Brett presented before examples with bubble chart. So this GeoBubble chart is the version of that function that will take into account all the features and properties of maps and projections and geodistances, etc. So again, we take data. In this case, it's going to be names and positions and petroleum production in barrels per day, and the flag image of the country of that here. So if we, let me open this. So we get something like this. So because we have 4 properties here, we get a list of tuples of length 4. So for example, for Albania, we would have Albania, some center position, this is the oil production, this is the flag, etc. And we notice that for some of them, we don't have the oil production. So we return missing, not available. So we have this function that will return those cases, and in the end, out of 240 or so, we will end up with 212, more or less. 212. We can now use GeoBubble chart to represent the data. And so we take all those 212 cases, and we take properties 2 and 3, which were positions and the petroleum consumptions. And so we are going to get these bubbles, and the tooltip is giving us the number in barrels per day. This is choosing the particular styling, the plot theme called marketing. It's using the rainbow colors so that different values have different colors and similar values have similar colors. And the shield projection, which is, it has this shape and has it's basically the joining of 2 projections above and below the equator. As a second step, let's now compute a quantile threshold at 75% and select those countries whose oil production is bigger than this threshold. And now we end up with 53. Now we will use callouts that were also introduced by Brett before. And we see, again, the bubbles with their names, which is being extracted as the first property from the data. And we use a different projection, the Winkel triple this time. Step 3, we increase the level here. So we now get only 31 of these countries, and we use flags instead of the names as labels for the bubbles. We get this map. And finally, we are going to use also a custom marker. This is this tank, a graphics of this tank. And we are going to use it here instead of the circular bubbles. And this time with labels again. Sometimes with callout, sometimes the label is on the marker. And the final map is this, which is a combination of what we saw before. We are using now the bone projection, and we are using the custom marker with flags. And sometimes, again, the flags are on the marker. Sometimes they use callouts. So you see how the use of various options allows a lot of flexibility in working with bubble charts. And the final function I'm going to talk about is geohistogram. This is also very useful to represent data on a map. And also, it has lots of flexibility via arguments and options. So for example, in this case, we start with data, which is the positions of trees in the area of Urbana-Champaign. So we have, in this case, 27,000 trees and their positions. This is the default map presented by GeoHistogram, and it's using hexagons to represent the density of trees in that area. And we can change colors and now use a different color function, in this case greens, same map. Or for example, we can now use the second argument to control the shape of the polygons used to represent the data, in this case rectangles. You can use also triangles, for example. As a final modification of the map, we can say add edges, in this case thin pink edges to those polygons, and we get this type of map. And as another example, here we have again data for thousands of breweries in the US. So we can plot them as points, and these are directives that will modify the result. So we are adding some opacity and the color. And we are restricting the map to the contiguous area of the United States. For example, we can now use a geohistogram of that data, and we will use now rectangles of size of 200 kilometers for those locations. And we get this other map. And we can combine both maps as usual in the Wolfram language with show, and we see their correspondence of the rectangles and the points in the map.